Welcome back to our series on statistical methods. I'm Mark Ledbetter. This is lecture 28, part A, and we are moving into chapter 10. And so this is no longer ANOVA or designs of experiment. This is regression. And regression is one of the most widely used statistical methods in all fields. So whether you're a data scientist, whether you're a statistician, whether you practice in another area of expertise and want to do statistics, this is a method that's almost required. So I hope that we give you a good foundation and help you be able to apply this in real life situations. So let's go ahead and get started. We're going to talk about first a simple straight line regression analysis. Y is going to be our response variable. That means it's dependent. You could also say it's the output of the process. X is our explanatory variable, and it's independent. And it is also could be called the predictor variable or our input. And little n is our number of pairs of observations. Remember, we have ordered pairs, what we call. So the data would look like x1, y1, x2, y2, and these would be coordinates all the way up to xn, yn. And I hope you remember a scatter plot. So here's an example of a scatter plot where y is on the y-axis and x is on the x-axis. So we're now going to talk about this as a model, all right? In introductory statistics, we looked at this as just the equation of a line, but now we're going to look at it as a random model, okay? So y, again, is our output variable, and then we have beta naught, and this is our intercept. So beta naught is the intercept, plus beta 1 times x. Beta 1 is our slope. Then plus epsilon, which is our random error, which is distributed as we assume normality, that it's normally distributed with a mean 0. That means all the errors average out to nothing, which is what we would expect, and with variance sigma squared. We could also rewrite this equation. We could solve for epsilon in the equation, and we'd end up with epsilon is equal to y minus then b naught minus b1x. And of course, we could rewrite this as y minus beta naught plus beta 1x, but we rarely do that. We like to leave it in this format here, because this, you'll see a little later that this actually tells us something. Okay, now we're going to go through an exhaustive list of assumptions. Some of these assumptions may seem trivial, but they are nonetheless there. The first is existence. So what we're saying that is for any fixed value of x, a random variable y with a finite mean and a finite variance should exist, with the mean being mu of y given x. Remember, we're fixing x. So for each value of x, we're assuming that there is a y variable that has a mean for that value of x. So it's conditional mean, mu y given x, and a variance, sigma squared y given x. So again, this notation tells us that y is dependent and changes with the value of x. That's what we're expecting. Okay. The second assumption is independence. The y values are independent of each other. Now this can be violated if we have multiple measurements made on the same individual, like blood pressure over time, and this is called longitudinal data or time series. So we use a different analysis methods to analyze dependent data. So we are in this class are only going to talk about independent data. All right. Linearity. So because we're using this model, which is the model of a line, okay, plus the error, and it's a straight line. So for this model, we're assuming linearity, a straight line model. Okay. Later on, we'll see that we can change that assumption to a nonlinear model, and that's fine. But for right now, we're talking about a linear model. And so the mean value of y is a straight line function of x. And we can write that as the expected value of y given x is set to some value, little x, is equal to mu of y given x, which is equal to beta naught plus beta 1 times x. And so here is an example, all right? Now, I didn't make this a straight line because I'm not good enough artist, but it's kind of close. So for value x1, we have a distribution. Remember that we're assuming that this distribution is normal and that this distribution has a mean here that's mu y given x1. Okay? And then for x2, we have another distribution of y, and its mean is mu of y given x2. And then same thing for x3 and so forth. For every value of x, there's a distribution. We're assuming that the distribution of y is normally distributed with some mean, y given that value of x. All right? So that's what we're doing. We're not just talking about one value. We're talking about multiple values we're talking about a distribution for every value of x. Homoscedasticity. Okay, so homo is the same, skedastic is scatter. So it's got the same scatter. Homoscedasticity, that means that we have homogeneous variance, or we have the same or equal variance across every value of x. So here we're saying that the variance of y given x is sigma squared y given x, which is just sigma squared. It's the overall variance. And we could write it using subscripts, so we could have sigma of y given xi squared or sigma y given xj squared, and we're saying that those are equal. Okay? So for every value of x, the variance should be the same. Normality is our fifth assumption. For any fixed value of x, a random variable y is normally distributed. This is needed for our confidence interval estimation and inference on the parameter values. If it's violated, we usually transform the data. We might take the square root of the x's, or we might take the square root of the y's. We might try either one. We might take the square of x's or the square of y's, one or the other, or both. It doesn't make sense to do both necessarily, or it might, but rarely. We might take the inverse, 1 over x, or 1 over y. We might take the log, and this is, again, the natural log. Or we might take the exponential of it, e raised to the power of the value. All right, so those are some of the transformations hopefully we'll have time to cover in this course. So now let's look at a plot. So I'm going to blow this up a little bit. And so we have this observed point here. And we have our regression line, and then we have the mean of the y's given x, okay? And so for this value of x, we have the mean. So the mean is given by the point on the regression line. And so the difference in y value between the observed value and the line, this is our error, epsilon. We might call it epsilon I for the ith observation or ith value of x. Okay? And so we have, in the y values, that's going to be y minus mu of y given x. This is also called the residual, right? Y minus y hat, we might remember. All right. The fitted value of y. And the population regression line, notice it doesn't have the error term. Okay. So x is assumed to be measured without error. This is important. The x values, we're saying that we're basically assuming there's no measurement error. Okay. which is not true, but it's true enough. It's close enough to the truth. Okay, but we're assuming that we can fix or set the value of x, and then we have to measure the value of y. X is dependent, x is independent, y is dependent on x. All right, so let's talk about our estimators. So for the parameter beta naught, we have beta naught hat, and for beta 1, we have beta 1 hat, and as you might suspect, for epsilon, we have epsilon hat. Now, epsilon hat is our residual, which is y minus y hat, and then we can rewrite this as y minus, you'll notice I have hats over the betas here. That's important. So it's y minus beta naught hat plus beta 1 hat times x. Notice there's no hat for x. We're not estimating x. We assume that we can measure x exactly. Okay? All right. So for n pairs of data, epsilon hat I hat is yi minus yi hat. And again, I'm just putting the I subscript and rewriting this equation. So how do we determine the best fitting straight line? In introductory statistics, we talked about the best fitting straight line, or least squares method. But now that we know calculus and we have a little more advanced class, we can actually show how this is done. Okay, so the least squares method determines the best fitting straight line as the line that minimizes the sum of squares of the deviations or errors or residuals from the line to the observations. Okay, so basically this vertical distance here, which is epsilon hat, let's say I, we're going to square them and add them all up, and then we want to minimize that value. Okay, so we're going to define this quantity q, and we're going to say that it's yi minus the mean of yi at xi. And we're taking the difference, and then we're squaring them, and then we're summing them up. All right, order of operations. We're rewriting mu of yi given xi as the line beta naught minus beta 1 xi. Okay, so right now we don't have any hats. We're looking at the epsilon values, not the epsilon hat values yet. Okay, so we're going to consider that q is a bivariate function, and not of x or y, of beta naught and beta 1. And so we can minimize q by taking the partial derivative with respect, let's say, to beta naught. And so when we take the partial derivative of this, remember that this is the sum. And so remember that if we have f of x plus g of x, that the derivative of the sum is equal to the derivative of the sum of the derivatives. So the derivative of the sum, which is a little messy, so the derivative of the sum is the sum of the derivatives. So the same thing applies in this summation, that we have the derivative, the sum of the derivatives is the derivative of the sum, dd beta naught, is equal to the sum of the derivatives. Okay, squared. All right, so that's what we're doing. And so when I take the derivative of this, I have to take the exponent, multiply it in the front, it's a 2, but then I have to use the chain rule, and take the derivative of what's inside the function with respect to, I'm sorry, this is beta naught, with respect to beta naught. And so this would be a constant. This would be a constant. So only this term would be a variable with respect to beta naught. So, and it's a negative. So that would, the derivative of that would be a -1. That's how we end up with the -2 here. Okay. Good. So I hope that makes sense. And it's a constant, so we can pull it out in front of the summation. And if you remember to minimize, find a minimum or maximum value, it's where the derivative, the slope of the derivative, or the slope of the line, the tangent line, is equal to 0. If it's a maximum, the slope of the tangent line would be 0. If it's a minimum, the slope of the tangent line would be 0. You can pretend I drew that correctly. All right. So if I set this whole thing equal to 0, I can divide both sides by -2. And when I do that, I end up just with this portion here equal to 0. And now I can, the sum of the differences is the difference of the sum. So I can distribute this sum to each element inside. And that's what I've done. So I've divided by -2 on both sides. And then I've said, okay, now I have the sum of yi's minus the sum of beta naught minus the sum of beta 1 xi. And since this is, there is no subscript I here, so I'm just adding up n of these beta naughts. So I'm just saying beta naught plus n times. So that's going to be n beta naught. Okay. Now, I can't do the same with this term because there's an xi here. But beta 1 can come to the front. Okay. And I can't do anything with this term because yi, it has an index I that we're summing across. And then it's still equal to 0, so I solve for the n beta naught now. And so that ends up being this expression here. And so if I divide every term, if I divide both sides by n to get beta naught by itself, well, that's the same as doing this and this. I can divide each term because we have a subtraction or addition in between. We can do that. Okay. Oops. Sorry. Now, hope it didn't flicker in the video like it did to me. All right. So when we do that, we end up with beta naught hat now is equal to y bar minus beta 1 hat, the estimated value, times x bar. Because now we're actually saying we want to estimate beta naught using this quantity. And so that's going to be an estimate. Now, y bar is not estimated, but it is for a sample. X bar is not estimated. It's x bar for only a sample. And so that means that beta 1 would be a beta 1 hat. It'd be an estimate. All right, that's it for this video. If you have questions, please make sure you come to virtual office hours. If you need help prior to office hours, by all means email me. But when you email me, if it's about a problem, then email me what the problem is, because I may not have it available, and then your work on that problem so far. If it's code, then by all means send me a copy of the code, and in the email tell me where you're having the problem and that you need help. And I will get back to you as soon as it's possible. Please take care of yourself and stay safe, because we want to see you here next time.